You can join the point with a line from the origin. This distance from the origin to the point is called r, and this angle this ray makes with the positive direction of x-axis is theta. So this is what you have seen in trigonometry, that there is a revolving ray and you measure the angle with the x-axis, positive direction of x-axis, and you take an angle counterclockwise positive. This is known, this is your first quadrant, this is your second quadrant, third quadrant, fourth quadrant. As your revolving ray rotates, your angle changes. But angle is always measured in counterclockwise direction with positive direction of x-axis. Now if you want to see this radial ray, this ray you can take a fixed magnitude like 1. It has a unit magnitude. It is your choice. Now you can draw a perpendicular from the distance, from the radial distance 1 you measured, draw it on the x-axis. Similarly here, you can draw it on the x-axis. Now we call this point as M, this point as P. Same, this is the point M, this is the point P. Now here you see your measuring distance. This is your y coordinate. This is your x coordinate. Here, this is your x coordinate. This is your y coordinate. Now x coordinate here is positive, y coordinate is positive. In the second quadrant, your x coordinate is negative, y coordinate is positive, because you are measuring from the your horizontal line x-axis upwards. You are going in the upward with the positive direction of y to reach your point M. So your y is positive. Now there is a concept. You like to find the ratio of perpendicular to the base. So what is that ratio? MP upon OP. So this ratio is known as tan theta. You keep increasing the ray size. Draw the perpendicular. So you will find that M prime upon P prime is equal to OP prime. So these ratios are constant. They just depend on theta. They do not depend on the length of the ray. Whenever you find such invariance, it is of value. It has importance. Similarly, you define a ratio called sine theta. Here you take length of the perpendicular, MP is the perpendicular, upon length of the ray, OM. Now you see this length, the ray length is always positive. This is always positive. Sorry. So it is length of a line. And MP here is positive. So sine theta is positive in the first quadrant. Tan theta, you see in the first quadrant it is positive because both perpendicular and base are positive. Similarly, cos theta is defined as base upon the hypotenuse or the length of the ray OM, which is always positive, so it is positive in first quadrant. Now my revolving ray has rotated by another angle theta. Again you are drawing the perpendicular onto the x-axis, like you drew it here. Now you see the length of the ray is the same as it was in the first quadrant, and your perpendicular value MP is same as before, and your x coordinate OP is now negative of same magnitude. Now what will happen to your sine, cosine? Your tan theta is perpendicular upon base. You see base is negative now in the second quadrant. I'm talking of the second quadrant. So you see your tan theta will be negative. Your sine theta is perpendicular is MP upon your ray size OM, so it is positive. Cos theta, you see, is your base upon hypotenuse it will be negative because your distance x is negative in second quadrant. So this is the way you see you can find the sines of different ratios in different quadrants. So here you will find that your sine is negative. You see, you take draw a perpendicular. Now what is happening? This perpendicular is negative. Base is negative. This ray is positive. Distance is always positive. Radial distance is always positive. So sine becomes negative, cos becomes negative, tan is positive. In the fourth quadrant, you measure your angle like this. So you see your angle is between 270 and 360 degrees. And again, your base is positive, perpendicular is negative, ray is positive. So you have only cosine which is positive, all others are negative. So just a little bit of trigonometry. Only thing you realize is that I am measuring angle counterclockwise positive, and that I am making with a positive x direction. Hello, hello. Class clear. हाँ बिल्कुल है. Now we talk about polar coordinates. So in polar coordinates, this is your x-axis, this is your y-axis. This is your r, this is your theta. So this is your x coordinate, y coordinate. So you say your radial distance is r square is equal to x square plus y square, or your r is x square plus y square under root. We take only the positive root. Theta you can say is tan inverse of y by x. So this is something, I think, enough information on polar coordinates. And based on polar coordinates, you can define unit vectors. Suppose you are using polar coordinates. What will be a unit vector in polar coordinates? Okay. So if I have to define a unit vector, how do you define a unit vector? We have got r theta coordinates. You are representing your point by r theta coordinates. So if you are representing a point by r theta coordinates, you can find equivalent x and y coordinates. This angle is theta. X you say is r cos theta. Y is equal to r sin theta. Just you know that base is x, perpendicular is y, and this distance is r. So you can define x and y like this. So how do you get a unit vector? If you just change the radial coordinate, r, so you're not changing theta, then your direction will be along this outward radial direction. So this unit vector you represent by ER. This is your radial unit vector. So one unit vector you get by just increasing r and keeping theta constant. Along this ray, theta is constant. Another unit vector you can find, you just change theta, but keep r as constant. Now if you have a revolving ray, it is going to make a circle. Circle about the center. About this origin, it is going to go in a circular motion. Now you are not changing your r. If you go along the circle, and you will increase your theta. So your theta will be perpendicular to this radial direction. So this vector is called E theta. This is a unit vector E theta. Suppose I am here, your radial ray is here. So this is your ER direction. And for, if you go tangentially to this radial direction, you can define your E theta. So if you are just rotating by a very small angle delta theta, and you get a direction which is tangential to the sun, while you are maintaining same radial distance. So these two directions are perpendicular to each other. You see, tangent is always perpendicular to the radius of the circle. Now these unit vectors are different from I, J and K. You see I and J, they always had the same direction. It will be always this direction for I, always this direction for J. But these unit vectors, they depend on r theta coordinates, and their direction keeps changing with r and theta. You have different theta, you get different direction. So with theta, this direction is always changing. These ER and E theta. So these are very important unit vectors, and you will see quite frequently in this course. So I have a radial vector ER. This distance is r. This angle is theta. So what is the unit vector in the direction of outward radial direction? If I take a distance 1 along the radius, base will be cos theta, perpendicular will be sine theta, because hypotenuse is 1. So my x and y coordinate becomes, this I can write as cos theta, sine theta. This is my x, y coordinates. So I am moving this ray in a plane, xy plane. This is my ER vector. My E theta vector will be, so this is a 90-degree angle. So what is the vector E theta making with the positive x direction? And then angle 90 plus theta. This much is theta, this much is 90 degrees. The overall angle made with positive x direction for this ray, for this direction E theta, is 90 plus theta. So you can say E theta is cos 90 plus theta, sine 90 plus theta, comma 0. So this is nothing but minus sine theta, comma cos theta, comma 0. So this is trigonometry, you already know. Not a big deal. You can just crack it out. Now we know ER and E theta. Now these are the two vectors in horizontal xy plane. If I take a cross product of these two vectors, it will come perpendicular to xy plane and in z direction. So you can call this unit vector in z direction as k. So your k will be, you have to take cross product of ER with E theta. So I will just explain what is a cross product, just to make the picture complete. If you have two vectors, A and B, so these two vectors, you join them, and you can define a plane in which these two vectors are lying. And how do you define a cross product? You take the smaller angle as you go from A to B as theta. So A cross B is defined as magnitude of A, magnitude of B multiplied by sine theta. This is the magnitude. And what is the direction? Direction is given by the right hand rule. So you get a normal vector perpendicular to the plane. To the plane formed by vectors A and B. These two vectors form a plane, and the vector will be perpendicular to that plane. You call that vector, unit vector, as n, and this is the magnitude of the vector. Geometrically, you will see, if you draw the parallelogram and you draw a perpendicular from end of this vector onto vector A. So this height is B sine theta, as this angle is theta. The product of magnitude of A and this perpendicular is AB sine theta. And all of you know that length of the base multiplied by the shortest distance between the two parallels, that is the perpendicular, this gives the area of the parallelogram. So this is area of this parallelogram. So that is the geometrical meaning of cross product. And this geometrical meaning is very important and is very important. It is comes handy. So cross product is basically gives us the area made by the parallelogram formed by these two sides represented by the vectors A and B, and the direction is given by the right hand rule. As your A goes towards B, you see here you are having a counterclockwise rotation, and the right hand screw will come out of the paper, out of this towards you. So that will be the direction. Now here you see XY plane, your Z axis or K direction has to be perpendicular to this plane, and so it is the outward direction. It is coming towards you as the right hand screw goes from X to Y in a counterclockwise rotation. Now I will explain cylindrical coordinate system. So cylindrical coordinate system is as good as polar coordinates. So what I do, this is typically represented like this. It is my choice. I say this XY plane, I take this direction as X, this as Y, this as Z. This is my horizontal plane. In most of the books you will see this kind of a presentation of cylindrical coordinate. So it is your choice. But you have to define a horizontal plane. And this is any point in space. You draw a projection from this point onto the horizontal plane. This is your projection. So what will be this distance from the point to the horizontal plane? Yes, anybody? Manish Kumar, what will be this height? We are given coordinates of this point. So this height is nothing but Z coordinate. You have drawn the projection from the point to the horizontal plane. So this height has to be Z. Now you draw projections. You draw perpendicular to the y-axis. So you have to go parallel to the x-axis. You draw a perpendicular to the x-axis, so you have to go to parallel to the y-axis. This is the way it is looking. This is a right angle. Now you can join the origin to this projection point. You call this distance R. So this R is not the distance from origin to the point. Call this point as P. So you have a projection here. So what is this distance X? First, I will ask, okay, this angle I call theta. I am making this angle theta from x-axis to this line joining the projection from the origin. So this x will be r cos theta. Okay. And this distance, so this is the length along the x-axis. This is the length along y-axis. This will be r sine theta. Now what are your coordinates? R cos theta, r sine theta, and z. This is the way you define the cylindrical coordinate system. So you are given a radial distance which is in the horizontal plane, and you are told that this is making an angle theta with x-axis. So you go along x-axis r cos theta, or what you do, you make an angle theta, you take a ray of length r, rotate it from x-axis, and you will come to this position in the horizontal plane. Then you move vertically upwards by coordinate z. So this is the way you reach your point P if you use cylindrical coordinate system. And how do you define your unit vectors? So you have got three coordinates r, theta, z. R, theta, z are the coordinates when we talk of cylindrical coordinate system. You are increasing your r, not changing theta and z. As you are in the horizontal plane, for example, here, you can only change theta. You can't change anything else here. So this is your ER direction. And when you change just theta, you go perpendicular to this direction, this is your E theta direction. And if you have to change only z direct coordinate, this becomes your K direction. So K direction is just along z axis. And you will find that ER cross E theta is K. This is what I had told just before this diagram I made. Nothing different. Again, you see ER and E theta depend on theta. I told you ER is nothing but cos theta, sine theta, 0. E theta is cos 90 plus theta, that becomes minus sine theta. Sine 90 plus theta, again cos theta. So these are my ER, E theta unit vectors. You see they depend on theta. Your K vector is independent. It is along the z-axis. So these are your cylindrical coordinate system. If you have any doubt in understanding it, you can ask. Then I talk about spherical coordinate system. You have to know all these coordinate systems. Because at times your problem is easier in one coordinate system than another. For example, you are having a circular motion in a plane. Then what will happen? Only your theta coordinate changes. R is fixed. So it is easy to analyze using cylindrical coordinate system or polar coordinates. If you use Cartesian coordinate system, what happens? Your x and y both are changing. So that makes calculations longer. Now you have a spherical coordinate system. Again, what I do is I define my xy axis like I defined for cylindrical coordinate system. Now I start with my point here and draw a projection onto the xy plane just like before. So I call my radial distance r as this. Here I call radial distance small r in xy plane. Now I am directly joining the point in question from the origin, and this distance I call r, and this angle you call phi. You have drawn a projection onto the xy plane and you join the origin to this projection. This angle you call theta. And this you can call P prime. So what is your OP prime? This is your z coordinate. If you draw a projection from this point P onto the z-axis, this will give you a z coordinate. What is your z coordinate here? Can you say this is r cos phi? And what is your length OP prime? Can you say it is
R sin phi?
Yes, very good. Now you know this length OP prime. Again, you have to find x coordinate and y coordinate. You draw parallel to xy axis. What will be your x coordinate? OP prime cos theta. So you'll get r cos theta sine phi. What will be your y coordinate? R sine theta sine phi. Basically, that will be OP prime sine theta. So r sine theta sine phi. So this way, once you know your point P, you can define in terms of three coordinates r, theta, phi. So this, why do you call them spherical coordinates? For example, this is your Earth. This is your equatorial plane. You can define your xy axis like this. Z axis like this. So you see, if you have any point here, this is making an angle theta. What is this direction? Is it called latitude or longitude? So this angle will go from 0 to 2 pi. So you see theta varies from 0 to 2 pi. And this is called longitude. And if you measure phi, this you are measuring from the z-axis. So this is your phi. So this goes from,
So 0 to 2 pi?
yeah, if you go along like this. So what is happening is, okay, you are measuring from here, then when you're having your phi as 0 degrees, you are representing your north pole. When your phi is 90 degrees, you are at the equator. These are your latitudes. 0 degree is your north pole. 90 degree is the equator. So there is a certain convention about these angles. If you want this, so you are in the northern hemisphere for this. Now, if you have any point here, you draw a projection onto the horizontal plane. So you will have an angle theta, and so your coordinates will be decided by r, theta, phi. Suppose you are here, and what happens? So this is a circle, kind of a circle here. Now, if I am here, I am drawing a projection. So again, I am measuring my angle from the x-axis. I have come to this position all the way. So this angle is theta, like this. But what is important is you are having a different value of, sorry, this is phi, a different value of theta. So you do not give any sign to this phi. The value of theta will decide your position, where you are on this sphere. So basically these circles which you are seeing, so they represent the value of the latitude. Can you see my point? So in the upper quadrant, you are measuring, you take it as a positive value. In the negative quadrant, you take this angle as a negative value. Okay. I'll have to just check it out. And if you spend time, you can even work it right away. So if you are here, I think I should make a new picture. This is done in a very standard manner to calculate the coordinates. So these are x-axis, y, z. Now you are supposing the southern hemisphere. This is a point. You draw a projection onto this plane. Okay. This is your z-axis downwards. So you are making certain angle with the z-axis. This is an angle phi. Here you have joined this. So this is your angle theta. This is your angle phi. If you call the angles in southern hemisphere as negative, maybe that will do the job. I have to check it out. Okay. How these r theta and phi are actually measured, how they are positive and negative. Theta is very clear. It is from the x-axis and going about this horizontal plane. It has to go from 0 to 360. And about this latitude, so you see here you have a latitude to make a circle. If you take a cutting plane, you are going to have a smaller circle. Biggest circle is the equator. As you go towards the poles, your circle will go to 0 radius. So whatever is your latitude, suppose you give this angle phi. What will be the radius of this circle? This is the radius of the circle. This distance is r. The radius of this circle is smaller circle. R sine theta. This z coordinate is r cos theta. This is r sine theta. Any point on this circle, now you can measure with the, call it the longitude. From the x direction, this is the x direction, you are measuring the angle. So you have got latitudes and longitudes. So this is your 0 latitude. I think this one is defined as 0 latitude and this is defined as 90-degree latitude, as we all know. So we should measure your theta, not from the z-axis, from the horizontal plane. If our theta is, sorry, phi. Somehow I am mixed up the angles. Earlier I was using phi for this and theta for this. So if we measure phi from the horizontal plane, then my latitude will be 0 at the equator and 90 degree at the poles. So now it is making better sense. You see, you are going counterclockwise, so it's a positive angle, and when you are going downward to the southern hemisphere, you are going clockwise. So you keep your phi as negative. So now it is making better sense. So your latitude, you take your angle phi as negative. If you want to reach a point in the southern hemisphere, if you want to reach a point in the northern hemisphere, you take it as positive. So there one more thing I like to tell is the unit vectors in spherical coordinates. So main trick about the unit vectors is you just change one coordinate. I have got this coordinates r, theta, phi. So I am just changing r. I am not changing theta and phi. So what will I get? My ER direction. If I just change only theta, you see how do I measure theta? I measure theta from the x-axis in the horizontal plane. So my E theta will be perpendicular to this direction. What will be my E phi? In E phi means I am just changing my phi direction. So what is my phi direction? This is a sphere. This is a circle. So I have to change only this angle. I am changing my E theta. Here I am just changing my theta. I am changing my E theta. So E theta will be this is the horizontal plane, and E phi. You see E phi. You are changing this angle, this cone. This cone you are changing. If you are changing this cone, angle of the cone, while you are keeping your theta as same, our radial distance is same, so you're going something like this direction, and you're measuring your phi from this direction. And here, so this E theta you see has to be like somewhere like this, and E phi. So you check it out. Main thing you have to see is some cross product rule has to be verified between E theta, ER, and E phi. So E theta cross ER, just let's assume E theta cross ER is equal to E phi. So you have to check it out. What is the right one? It has to satisfy the right hand rule. For cylindrical coordinates, what we found was ER cross E theta is equal to K. If you just cyclically change R theta coordinates, so you write R theta K, you cyclically change that, just like you do I and J. ER becomes E theta becomes K becomes ER. This kind of a change you can do. Now ER becomes E theta will become K cross. This will be ER is equal to E theta. This way you can write all the cross product rules for cylindrical coordinates. Similar thing you can do for spherical coordinates. Now, how do you define a position vector? In rectangular Cartesian coordinate system, you just define it by x, y, z. So this is a position vector. Suppose P is your point x, y, z. This is what we will show. In cylindrical coordinate system, what was your coordinates? R, theta, z. So how will you define your OP? First, you will go in the horizontal plane. In the horizontal plane, you are going along the radial direction. So if you go a distance r in the radial direction, ER, then you go upwards in the vertical direction. You are going perpendicular to the horizontal plane. So this is your position vector in cylindrical coordinate system. In a spherical coordinate system, what is your position vector? Your position vector is simply the radial distance r and this direction ER. You have directly gone along the radial direction to your point. You have directly gone from here to your point, distance capital R, and you have moved in the radial direction along the ER direction. So your position vector is just this distance R, ER. While you were in cylindrical coordinate system, you first went along this direction E, small ER, distance R, then you moved vertically upwards by distance Z along Z direction. So you see your different position vectors are there in different coordinate system. So if you are dealing with spherical coordinate system, you see you have got only one direction to worry about. Here you have got three directions to worry about. Here you have only two directions. So depending on the situation, suppose you are restricted to a plane, then you will prefer cylindrical coordinate system because you have to just change R. Only R and ER, only one coordinate will tell you your position in plane. And if you are restricted to a spherical surface, for example here, your R is suppose fixed, you are only dealing with one coordinate, R and ER direction. Now this ER direction will have all theta phi. So somewhere it will make your life easy. So let's see, we will do different problems dealing with different things. So this is just a course of introduction in mechanics. I am just reviewing your mechanics for further use in solid mechanics. So I think I will cut it out today here. Any questions?
सर जो ये एंगल है फाई, ये तो
Yeah.
Z से बनता है, R पे मतलब प्रोजेक्शंस जो हम लेते हैं वो वहां से बनता है.